Hello, everyone. My name is Miranda.
My name is Emma.
My name is Jing Yang.
And today we'll be sharing our project that we've been working on this summer. So before we go into details about what our project was about, we want to introduce the team that we've been working with at UBC. And more specifically, we've been working with the Office of Enterprise Risk and Assurance, or more specifically, the Enterprise Risk Management Team, or ERM. This team works at identifying, assessing, and managing risks that affect UBC and its students and employees. They transform this information into actionable steps that help protect the university and its strategic goals. And they meet and collaborate with leaders at UBC to walk through these steps. Now, to look a little bit more deeply at what this current process looks like for gathering this risk-related information, the team mainly talks to personnel at UBC to gather this information. And currently, they put all this information into what's known as a risk universe, where they have risk names, descriptions, and drivers, as well as a subset of other information. To make this a bit more concrete, though, one example for a risk name might be extreme weather events with this description here, and one of the drivers might be climate change. But this isn't the only piece of information that they can use to acquire all this risk-related information that might affect UBC. They also gather this information through industry and research reports. These reports usually come out annually, and they might look something like this, where they're really geared towards different corporations, business, and universities, and the risks that might affect them. But there's also another type of information that might include this risk-related information, which includes just regular news articles that go over different risk events that might affect these risks identified in these other industry research reports. So this poses a problem. As risks continue to evolve at a rapid speed, how can the ERA team continue to keep up with these emerging threats? You can imagine how long and time-consuming it might take to get through all of these reports. Some are somewhere between like 100, 150 pages. So this takes a lot of their resources away from doing other important tasks. And so we propose a solution to automate this process by identifying potential university-related risks from the textual data.
So as previously mentioned, the ERA team works with lots and lots of text data. So one way that we can automate this process is through the usage of large language models. Large language models are trained with self-supervised machine learning on a vast amount of text. They're designed to understand and generate human language for a wide range of NLP tasks. Most of us are familiar with some popular LLMs being ChatGPT, Gemini, and Claude. And this is where you can ask in a prompt for the model to do something, and the model will return a response accordingly. So the ERA team has already started automating this process through LLMs, where they took the PDFs, extracted the text, pre-processed it, and fed it into a GPT risk analysis. The GPT risk analysis looks a little something like this, where they asked in a prompt to extract all risks that were mentioned and the fields and what they mean. From this model, they got an output in a JSON file of a dictionary of all the risks extracted and the corresponding fields. Throughout the summer, we've been working and exploring on how to enhance the current pipeline. So the first one to tackle was to enhance the GPT risk analysis portion. But we also implemented a way to evaluate the models and the prompts we work with, and flagging the ones for human inspections that failed. And what wasn't tackled before was the news article data, and so we incorporated a pre-filter, a web scraping tool to extract the text, and a binary classifier to detect whether or not this article was actually risk-related or not. The ones that passed were summarized, and ultimately at the end, we explored a way to link the PDF and the website articles together.
Regarding our workflow, we will start with the enhanced GPT risk analysis. So how can we enhance GPT risk analysis? To get an enhanced output, we can first enhance the input, and the second, enhance the process, and in this case, is enhancing our prompting. So we have two ways to enhance the input, file input and file search. And we have explored 5 ways to enhance the prompting. And today we are going to be talking about few-shot learning, choosing a model, and a two-pass approach. So traditionally, there are two ways of input, text and the image. And we just wonder, like, is there any other input option that we can explore? So there comes file input and the file search. So how file input works? First, we got our PDF, and then we extract text from this PDF. At the same time, we take a snapshot of each page in this PDF. And we are putting text and the image all together into the model. So take the PDF as an example. And this will be the snapshot of a page in this PDF looks like. And this will be the extra text will be look like. So as we can see, like this page is full of diagram. So if we are only taking the extra text and put it into the model, it won't be able to capture the whole picture. And file input enables us to take both the text and the image and putting them together into the model, and that can like greatly enhance our output. And here is how file search works. So first we have our document, and they will be uploaded to the model. And the model will first do the chunking, and after chunking the text into smaller chunks, it will use an embedding model to vectorize them, and all of them will be stored in a vector database. And after the user prompt the question, the model will do a similarity search, and it will retrieve the most relevant chunks. And based on that, the models will generate a response for the user. So this is essentially a RAG system. And moving forward to prompting, this is what the current ERA team's prompt looks like. So to enhance the prompting, we introduce few-shot learning. So few-shot learning enables you to steer a large language model toward a new task by including a handful of input-output examples in the prompt. So rather than fine-tuning a model, which will require tons of human label data, few-shot learning enables the models to implicitly pick up the patterns from the example that you provided, and they will apply it to the prompt, and based on that, generate the output. And this is what our current prompt looks like. And we use Markdown to divide the long prompt into different sections. And below we provide an example to the model and for it to better understand what we expect in our output. So the ERA team currently is using a reasoning model. A reasoning model will provide better results on tasks with only high-level guidance. And here is a list of GPT models. GPT models will benefit from very precise instructions. And given that we are providing a long and a detailed prompt, we choose GPT 4.1 mini model as the best model for performance and cost. So during our risk analysis process, we run into a problem. Like, even within the token window limits, information from long PDF is not fully extracted. So our proposed solution to this is a two-pass approach. We first for risk count, and the second one is for risk extraction. So the two-pass approach looks like this. Like first, we pass the PDF to the model and ask how many risks are there in the file, and the models will output a number. And then we pass the PDF into the models again and ask extract the 7 risks in the file. And this time the model will output a list of risks with all the detailed information, like risk description, risk names, risk drivers that we want to have.
Next, we added a model evaluation portion of the pipeline. This not only just flagged different reports that seemed to be below a certain threshold, but we also used a couple of these metrics to be able to compare the original pipeline we were given, as well as comparing them to these enhanced things that we were doing to the GPT risk analysis process. And so there's a number of different metrics that we use, but I'm only going to share 2 of them today. So the first one is going to be a consistency test. And so what we haven't talked about previously is that using GPT models can result in using the same prompt on the same report, there might be different types of results. And so we wanted to evaluate whether the prompts were returning consistent results even given the same prompt. And so what that process looked like is that we asked our LLM or a GPT model to find the risks with the same prompt on the same different PDFs. And then it returned a JSON file, something similar to what we saw earlier. But again, that's textual data. So then what do you do with this textual data to be able to run some calculations on it? You can use a word embedding model that's going to represent words as numeric vectors so that you can run something like cosine similarity that it allows us to ask how close the words are to their meaning between all these different JSON files. Because we're doing this multiple times, we can aggregate or average across all of these responses so that we can have a single consistency ranking for each of the PDFs that we go through. And then we can see if it meets a certain threshold. Through trial and error and just looking at the responses that come out, we decided that 0.85 was a good criteria for consistency, and that's what we used. And so just to kind of show you what the original prompting versus the file search and input that we, or file input that we explored with, I have the consistency score from a 0 to 1 on the x-axis, and then each of the risk analysis methods along the, the x-axis. And here you can see that between all 3 of the items explored, they're relatively the same. File input is a little bit higher, but again, overall, these methods are quite similar for their consistency score. The other evaluation metric that we'll actually show you today is whether the model returns accurate information. It's all fine and good that these are consistent scores, but are these accurate information that it's actually returning? And so the ideal process would be to use humans to be able to show us what the outputs look like and compare that with model outputs. However, we run into a problem where we don't have ample human labeled data. You might be wondering, we started this whole presentation talking about how this used to be a manual process. But if we think about what the human data looks like, it's in this risk universe, and it's aggregated across sources, different years, and PDFs, and it includes lots of conversations with UBC personnel. Whereas with the model data, each source produces its single input, and the content of this looks a little bit different because it's based on the textual data alone. So this doesn't really lead itself to be a good comparison or source of human labeled data. But that's okay. There are some other metrics. We can use LLM as a judge that we saw earlier. Then this model can just be a proxy for a human evaluator. There's some research out there that models like GPT-4 can rank model outputs similar to human reviewers. However, others express a lot of concern about using this as a model to judge other models like itself. Again, using GPT-4 to address or to see the output of like another GPT model might impose some biases in there and overinflate their scores. Another thing that we were talking about with consistency is that GPT models might fluctuate in what kind of responses they give. So one way you can combat this is use an aggregated or aggregate across multiple LLM responses that are used for evaluation instead of a single response. So given the literature and these ideas, how we implemented these steps was we used our LLM to find the risks, to get the JSON file that has all of the risk-related information. And then we ran another LLM to evaluate it 5 times and to get a little bit of a report card at the end. To show you a little bit about what the prompt looks like, here we have that the prompt is being asked for a summary of factual faithfulness. We gave it a ranking of 1 to 5 and provided some details of like what would a 1 be versus a 5. A 1 would be that it's completely unfaithful based on having 7 or more discrepancies, whether a 5 would be that it is faithful. And then here is an example of what the output would look like. It not only gives us what the verdict and that ranking would be, but also asks for justification so that human observers can look at this and see exactly what the model was trying to, I guess, think when it gave this ranking. Again, I have factual faithfulness here on the y-axis and then the risk analysis methods here. And for our findings, we see that the original and file search are quite similar, whereas file input is a little bit lower. Each of the dots are different PDFs. However, if we think about appropriate benchmark, looking at some of the output, we think that 4 or 4.5 might be a more reasonable benchmark of what actual like factual faithfulness should look like. And so we think that all three of these methods a little bit subpar to what other methods might suppose. I also have some issues with maybe using LLM as a judge or what we used as our reference text. So if you have more questions about what that looks like, I'd love to answer that in the Q&A.
So in the end, we have successfully improved our PDF risk analysis. First, our pipeline is more stable. So in terms of input, for file input and file search, we restrict the model's input to the uploaded file. And in terms of prompting, since we are using a two-pass approach, it breaks down the entire extraction process, and it's easy for us to spot issues. And we indeed have had a better result. We managed to extract more risk with details, especially for long PDFs. So here is a table of a number of risk extracted. So as we can see for the two long PDFs who are like over 100 page, like the file input and the file search performs better than the original one. And based on all of our findings, our recommendation is using a file input two-pass approach. Since it is the most stable one, like it has the highest consistency score, and also it outperforms the other two.
So now we'll dive into the website branch of our pipeline. So to start off with, we were provided with a list of URLs, and some of them having keywords to refine the search, and some of them not having any. So we've incorporated a pre-filter, which essentially takes an article, and we extract the title of it, and also the corresponding keywords, and we calculate a cosine similarity between them. If it's above a certain threshold that we set, we'll pass it on for further analysis, but if not, it's discarded. So unfortunately, in this case, the BlueJay sweep was discarded. With the extracted text, we now pass it into a binary classifier. What this classifier looks like is we'll take all the articles that we've extracted and try to determine if it's actually risk event or not. This is where we introduce an encoder-only model. This is quite different from the GPT models that we've worked with up until this part of the pipeline, but some of these strengths are that they're open source, so they're free to use. They can be executed locally, so it minimizes data privacy issues. And also, when well-trained, it will outperform decoder-only models. However, with these types of models, it requires labeled data. So we had to manually label about 105 articles, but we felt this was insufficient. So we leveraged a GPT-4o mini model to help us label our data. So this got us about an extra 120 articles. The type of encoder-only model that we used was a semi-supervised learning model. So as a high-level overview, semi-supervised models work really well when we have a small subset of labeled data and a large amount of unlabeled data. We feed both into the model, but we predict on the unlabeled data and train on the labeled. And with each prediction, it has a probability on how confident the model is in its prediction. With whatever threshold that we set, if it's greater than that threshold, we feed back the high confident prediction back into the model to retrain and predict again on the rest of the unlabeled. And this process happens iteratively until we have no more unlabeled data left or if a certain evaluation metric drops. So with that, we created a balanced data set, and we've explored a lot of different models, but ended up using a cat-boost binary classification model. With this, we got a false positive rate of about 0.182 and a false negative rate of about 0.019. Through training this model, we really tried to minimize our false negative rate because in the context of our project, we really wanted to capture as many articles as we could that could be of potential risk. However, these statistics were under a decision threshold of about 0.19. So this threshold was calculated and optimized to balance the trade-off between precision and recall, And as you can see, 0.19 is not a good representation of a strong classification model. And this is solely due to the limitations of our training data. The quality of our training data was very limited because we manually labeled the data. We're also not domain experts. So this introduced a different level of ambiguity and a wide range of topics that were included as risk-related or not. In addition to this, the size of our training data was also limited with about 225. And given the range of the textual data, we felt this was insufficient to actually train a super high performing model. So with that, we introduced an alternative classifier where we actually leverage the GPT-4o mini model prompt that we used prior to help us label our data. So this is the current version that is implemented in ERA's workflow.
And then lastly, we wanted to bridge our PDF side of the pipeline with all of the news articles. Again, we have a long list of different risk names and risk descriptions, and we would like to be able to pair these risk events that are emerging in the online news sources with those risk events. And so before we can do that, we wanted to put our online articles in a similar format to what those descriptions would be. So we wanted to summarize those articles first. And so for summarizing an article like this, we used a two-prong approach. We first extracted relevant sentences using BERT, or an extractive summarization method, where we just took a bunch of the most important sentences or phrases verbatim from the original text. And then to make sure that it matched more of a paraphrased format of what our risk descriptions would look like, we did the second part where we summarized the extracted chunk using BART, or an abstractive summarization method, which creates more paraphrased sentences, again, to link those and be in a similar structure to the risk descriptions. And then for the article that we were just working with, this would be an example of what that summary might look like. And then lastly, we wanted to link these summaries with the risk descriptions we've identified in those industry and research reports. And then to do that, we have our list of risks and their risk descriptions, as well as the online article summaries. And we leveraged what we used earlier on in this presentation, where we used word embeddings to turn the words into numerical vectors, use cosine similarity to see how close these risk descriptions were to the summaries of the online articles. And then through trial and error, we picked 0.8 as a benchmark through reading some of the responses. Again, there might be tons and tons of articles over time that might be linked to certain risk descriptions and the summaries. And so if it exceeded 10, we only took the 10 highest with the 10 highest cosine similarities to be linked to the risks and the descriptions. And then for one example of one of the risk names of cybersecurity, it was linked to this website here.
So based on our work, we have several recommendations. One key takeaway is have a domain expert label a subset of data throughout the pipeline process. So first, if there is a domain expert from the ERA team, can label a subset of PDF and extract risk name, description, etc. And that can enable us to use an encoder-only models for risk analysis. So as mentioned before, decoder-only models, i.e. GPT models, they have their own weaknesses. So for example, model discontinuation. So right after we completed our coding part, the OpenAI released GPT-5. So OpenAI has control over the life cycle of their models. And if they choose to discontinue the one that we are currently using, there is no way that we can do about it. And also we have a talk about the privacy concerns and about it is a closed source model and its inconsistency. And plus, because it's a decoder-only models, it will always hallucinate. So encoder-only model can bypass these issues, and if they are well trained on human label data, they can outperform decoder-only models.
Another part of the process that would benefit from some human labeled data was in our evaluation step. So the ERA team, we suggested the ERA team might evaluate a subset of the risk analysis reports that are being outputted by the GPT model or whatever model they use in the future. And this would allow for a human in the loop approach in the evaluation process. Again, we can still use LLM as a judge over most of the reports, but even being able to compare these to a subset of the human evaluation might enhance this a lot further.
And lastly, if we had the ERA team to label more website content as risk event or not, it'll help increase sample size, but also the precision in our training data set. This will allow us to build a stronger classification model, maybe one that's larger and a lot higher performing on the textual data that we work with, and in terms of better precision and cost and more time efficient. So in conclusion, throughout the summer at the DSSG program, we have enhanced the prompts that were originally in the workflow. We've also implemented a way to evaluate the models and the prompts we work with. We tackled the website data through a web scraping tool and found a way to classify the website articles to refine the volume of content we work with. And in the end, we found and explored a way to link the PDF and the website content as our final product.
And our project benefits social good as it can help identify risks that will help protect university students and employees.
And not only in the content of the work that we were doing, we were also thinking about how we can impact social good through the process in our pipeline. And so we thought whenever possible to use smaller and more cost-efficient components of our pipeline. This included introducing a classifier instead of using more powerful models, as well as cheaper GPT models whenever we could. We weren't able to talk about this in great detail in this presentation, but do so more in our report where we provide suggestions on how to fine-tune a smaller encoder-only model that will hopefully allow for privacy, as well as, again, minimize those extra costs of these larger GPT models throughout the process. Thank you.